Hi everyone, my name is Sam Lane and today our presentation will be on maintenance and the end of PV systems, the end being the end of life. So our references today, um, I will be using the NREL best practices for operation and maintenance of PV and energy storage systems. So most of the information will come from section 6.6, 6.7, and 6.10. Will be those sections from that textbook. So the first thing we're going to cover is preventatives and scheduled maintenance. So the purpose of any preventative scheduled maintenance system is to maximize the system output while at the same time lowering your cost. So keeping the cost as low as possible by one, minimizing the amount of preventative maintenance you do. So you want to find that optimum amount, right, where you're going to prevent those more expensive failures from occurring, while at the same time um, minimizing the amount of maintenance that you have to do to lower your OPEX, your operational costs. And so, by doing that, by doing preventative maintenance, you're going to maximize system output, maximize system life, and like I said, you're in that balance between cost of maintenance, yield, and cash flow. So the protocols depend on system size, design, and complexity, and a lot of these protocols will be called out in the manufacturer's guides. So manufacturers a lot of times will provide guides to the operators, and then it's kind of up to the operators to make it happen. So another key point with this is that you really got to think about preventative maintenance during the design phase. So the picture here is a battery storage system. And they budgeted 100,000 a year for their O&M on the storage system. But that would likely be a lot more if they didn't think about in the design phase, how to make sure you had easy access to the different strings in the different battery cells. So designing that access in to make it easy in and out really lowers the cost of that maintenance. So next we have corrective maintenance. So unlike preventative maintenance, this is something, this is what you're trying to prevent with preventative maintenance. But corrective maintenance is definitely going to come up. And when it does, it's important to complete the maintenance as soon as possible because most of the time, right, when you think about corrective maintenance, this is stuff that is keeping the system from operating or, worse, something that would be of a worse consequences, something that could, is affecting personnel safety. But anyway, nonetheless, downtime equals lost revenue. So if something comes up, you really got to be aggressive at getting the corrective maintenance done. So a lot of times, response time should be specified in the contract, and so here we're talking about larger commercial projects. So for those larger projects, right, where you have, you know, lots of times the you're hiring out your maintenance, right? So in that contract, um, if you have something corrective come up, you want to make sure that the timeline is specified in the contract, and that's typically less than 10 days. 10 days of downtime could be a lot of lost revenue. So not only the timeline needs to be in the contract, but also funding options. So how much it's going to cost and how you're going to fund it, and kind of planning that out. Um, and so again, we're back to you have to balance those maintenance costs and the lost revenue. So especially for smaller systems, so for residential systems, let's say, if you have one module down on a residential system, something's is damaged and it needs to be fixed, needs to be replaced. It might not make sense to bring a whole truck out to fix that one module. It might be more expensive. So if you are the company responsible for working on those modules, you might wait until you have 10 different modules to fix, or maybe 10 different homes when you're talking about residential systems that you need to go out and fix before it actually makes financial sense to go fix it or go make repairs on it. And then again, if it is a safety concern, it's something that needs to be addressed ASAP. So kind of differentiate between safety and then just trying to maximize costs or maximize revenue. Sorry, minimize costs. So warranties, I'm kind of going right along with the corrective maintenance piece. Warranties cover materials and workmanship, and they protect the purchaser against failures from material defects. So these a lot of times we're talking about material defects that happen in the manufacturing process that aren't uncovered until it gets out in the elements, stuff like that. Most manufacturers provide 10 to 12-year warranties, but some are as low as 5 years and some are as high as 25 years. And then the common term for inverters these days is 10 years. So the inverters kind of have a similar lifetime to batteries, a lot less than the typical lifetime of PV system. And so another thing warranties do is guarantee certain power output, and they also factor in that natural degradation of the panels. So over time it's going to go down, and that's factored into that warranty figure or warranty number for system output. One thing to keep in mind though is financiers are oftentimes wary of warranties due to the high risks that they present. So a lot of times financiers aren't going to take into account warranties when they're thinking about lending money or things like that, unless it's the warranties offered by a larger, more reputable and diversified company that they're confident will be able to follow through with the warranty terms. So moving on to the next section, end of performance period, so end of life. So there's 4 main options at the end of life, and here we're talking about the PV system. So you can refurbish the system and extend the life. You can extend the contract or PPA terms, and that's, if the system's still operating fine, that's good. You can sell the system, which that could impact the system warranty that we just talked about. And you can also remove the system and restore the site, try to make it like it never happened. So those are your 4 options there at the end of life. And then so, when we talk about PV system life, we just threw the 25 year term in there, but there is some evidence that PV systems could last longer. And there's some industry guidance right now that's suggesting 40-year analysis period is more appropriate. And as more PV systems start to age and they start to get closer to that 25-year, that 40-year point, we'll have a lot more data and be able to really, just have more data, more sites to point to for how long these systems are lasting and what their power output is towards the end of life. And then also RCRA, the U.S. Resource and Conservation Recovery Act. So this codifies waste practices and assigns responsibility to the waste generator, and that this goes far beyond PV systems. This is what pretty much all industrial sites across the U.S. are using to define their recycling and reuse and waste practices. So best practices minimize waste and design for recyclability. That's what this act is designed to promote across the industry. And then it's also important to note that 84 to 90% of PV waste can be recycled. And then we'll look at an example of that here in a second. So First Solar, it's a module recycling company. They can cover up to 90% of materials. That includes semiconductor and glass materials. And they are continuing to scale as more systems reach that 25-year age and we're able to recycle those components. So check out that article or check out their website. It's, and that's what First Solar, obviously a big solar manufacturer, that's what a lot of solar companies are turning to. Obviously if they can get the panels back, it could definitely be cheaper, if they're able to optimize their process to recycle rather than sourcing new materials. So battery end of life. So batteries, like we've already kind of mentioned briefly, lose their capacity and efficiency over time, much quicker than PV modules. So we're talking about 1,000 to 2,000 cycle lifetime for lead acid batteries, and then 10,000 cycle lifetime for lithium-ion batteries. So that 10,000 cycle lifetime for lithium-ion, that might be 8 to 10 years depending on how you're using the battery. And then they have that gradual reduction in capacity over time. So battery recycling and reuse. So like I said, battery replacement 2 to 3 times during the 25-year PV system lifetime. Lead acid, it's much easier to recycle due to regulations with lead being toxic. That's kind of created a situation where industry has to recycle lead, not just in lead acid batteries. So that kind of push. There's pathways to recycle lead, so it's easy to recycle those types of batteries. And then 65% of lead acid batteries is heavy metals, including lead. So it's a lot easier to recover that than mine it, or a lot cheaper anyway. Lithium ion, less regulated, more complicated to recycle. It's a little bit newer technology. There's also, so many different sizes of lithium-ion batteries, from cell phones all the way up to giant energy storage systems, at the utility scale or at the commercial scale. That can be tough. It's a tough, it's a problem that's being tackled right now. And going forward, I think definitely economics will drive more recycling in the future. So a company to look at for this is Lithium Cycle, or LI Cycle. So check out this really good article about kind of what that company is doing. It's a new company in Canada. They have projects underway in North America, Europe, and Asia, and they are creating a secondary supply of materials that would otherwise be mined for these lithium-ion batteries. And they're doing everything from those cell phones all the way up to large batteries, and they're expecting a lot more batteries coming in with EVs scaling up, and then we'll start to see larger energy storage projects, on these, utility scale PV systems. So there are definitely companies out there that are working to make those economics work for lithium-ion battery recycling. And that's the last slide. So I hope you enjoyed the presentation. Thanks.